Welcome to my channel. In this video, we are going to learn about p-n junction. Now, it is a basic building block for all the semiconducting devices which contain one or more junctions. Examples: diodes, transistors, etc. Now, these are semiconducting devices. For example, diode, you have one junction. Transistor, you have two junctions. So, basically a p-n junction is a control element. It is a control element which actually used to analyze the behavior of all these semiconducting electronic devices. So, junction behavior is important to analyze these electronic devices. Now, in this discussion, we will see first how the junction is formed. We will briefly discuss about this. Then we will discuss how junction behaves or properties of these junctions under two conditions. One I will discuss in this video: with no bias, that is no external bias, means external applied voltage. So, with no bias, it is also called as open circuit p-n junction. It is also called as open circuit p-n junction, and this I am going to discuss in this video, and we will also discuss in next video the junction with a bias. And there you have forward bias and reverse bias. So, we will confine our discussion only to this particular point in this video. Now, there are different methods of forming a p-n junction. One, by alloying. Number one, by alloying, or number two, example I am just giving, by diffusion. So, there are many others, but basically, now what do you mean by alloying? Suppose say I take a p-type silicon and add a pentavalent impurity. A pentavalent impurity. So, when I add a pentavalent impurity to a p-type silicon, partially I will have n-type silicon, such that a p-n junction of silicon is formed. So, here it is actually alloying, and then we will discuss how this junction behaves. Now, as I said, I am going to discuss with no bias. With no bias. So, the points or the properties that I am going to discuss for this junction are like this. So, we will come across these points: diffusion, drift, depletion region, electric field, barrier potential, so these are the points that we will now discuss in understanding a p-n junction. Now, we know that Let us take this example of the diagram for a p-n junction. Now I have a metallurgical junction formed like this between p-type and n-type. So this is p and this is n. In p-type we know that majority charge carriers are holes. That means NH is greater than Ne, and in n-type the majority charge carriers are electrons. So Ne is greater than NH. Now in p-type what do we have? We have acceptor ions which are negative ions. So these are the acceptor atoms, ionized acceptors, and you will have holes, they accept. So you have holes which are majority, So these are all acceptor and holes which are majority. And now I will consider for electrons this one, filled one. So you also have, due to thermal agitation, you also have minority carriers, and here minority are electrons. So few electrons you will have. And when it comes to n-type, you have positive ionized donors. So these are acceptors and these are donors, and they donate electrons. So you will have free electrons. So you will have electrons. So these are all electrons. So electrons are majority. And what are minority? Minority are holes. So you will have minority holes. So less number. Now what will happen? Because here holes are more in number in p-type, holes are less in number. So more here and less here. Holes are more here, less here, and therefore there is a concentration gradient. That means higher concentration of holes here and lower concentration of holes here. So from higher to lower, the charge carriers will move. Which charge carriers? Majority charge carriers. So what are majority charge carriers in p-type? Holes. So holes will move from here to here. Thereby what will happen? They recombine with these electrons. Thereby what will happen? There will be these charge carriers, a layer of these positive ionized donors will form here, which become immobile, which means basically they are tightly bound to the lattice with the surrounding atoms. Therefore, because there are no free charges, they recombine, so they become immobile, a layer of positive. So this is a layer of positively charged space charge region. Now when holes from n side, here you will have now electrons more in number and here electrons less in number. So when electrons move from this side, from n side to p side, majority electrons move from this side to this side. So these electrons will recombine with these holes. So these electrons will recombine with the holes. So what will happen? That means in both sides the majority charge carriers will move across the junction like this. So electrons will move in this direction and holes will move in this direction, as I have shown you with the black arrow. So what will happen here? The negative acceptor ions will now form immobile charges here. So there are no free charges, and therefore there will be a potential difference developed. So this is what this is, a layer of negatively charged space charge region. Space charge region. And these two put together will form what is we call it as depletion region. What do we mean by depletion? Emptied. There are no free charges. So there are no free charges, and these ions, acceptor and donor impurity ions, are immobile. And so you have a separation between positively charged layer and negatively charged layer, and this will form a depletion region. So this is what is called depletion region. Why it is called depletion region? Because there is no further movement of free charge carriers in this particular region. That means it is completely emptied of free charges. Emptied of free charges. Therefore it is called depletion region. Now, because there is a positive charge and negative charge in this particular one, there is a separation between positive charge and negative charge. There will be a potential difference developed, and that potential difference, I will write it as V naught. So this V naught is developed, and the width of the depletion region, I will write it as W. Width of the depletion region, I will write it as W, and this is V naught. Now, the process of movement of these charges, majority charges, is what is called the process of movement of majority charges across this region due to non-uniform concentration. That means concentration, there is a change in concentration level. Concentration gradient is called diffusion. So this process is called diffusion. And because of the movement of charge carriers, there is a current flow. So that current, so movement or motion of these charges due to this process, due to this diffusion, is called diffusion current. Diffusion current. So now let us see how diffusion current is here. So here it is hole diffusion. Hole diffusion. Therefore in this direction hole diffusion current. And now here you will have electron diffusion. Here in this direction electron diffusion. That means hole diffusion is from p side to n side, and electron diffusion is from n side to p side. So we have this electron diffusion and hole diffusion, and that's how you have the diffusion process and diffusion current. Now once, because this depletion region is formed, usually this diffusion is large. But once this diffusion is formed, what will happen? There will be a potential difference, and because of that potential difference, I will write it as V naught. There will be a width of this depletion region, and because of this potential difference, there will be an electric field developed. Electric field developed, and I will write that electric field as E. So electric field developed between these two is what we call it as E. Now, the potential V naught, this potential V naught depends on the type of the semiconductor. It depends on the type of the semiconductor, then amount of doping, it depends on the amount of doping, and also the temperature. And the width of this depletion region will be very small, usually, that means the thickness or width, I will write it as width, is usually very small and of the order of 1/10. That means very small means thin compared to p type or n type material, 1/10 of a micrometer. So that will be very small, 1/10 of a micrometer. Once this is formed, what will happen? It empties the free charge carriers, means the diffusion stops. That means this acts as a potential barrier and prevents the further movement of free charges. Therefore, we called it as potential, barrier potential. So, this is also called as, this potential acts as a barrier for the further movement of charge carriers. Therefore, V naught is also called as barrier potential or built-in potential. Now, because of this electric field developed, what will happen? Let's see. Because of this electric field developed, which is directed from positive charge towards negative charge. Due to this field, minority charge carriers will move on either side, which means if it is p type and if it is n type, then here minority charge carriers in p type are electrons and in n type holes. So, these are minority. So, what will happen? These minority carriers, because of this electric field developed across this depletion region, will move on either side. That means electrons will move from p side to n side. So, electrons will move in this side and holes will move in this side. So, holes will move from n side to p side. Therefore, this constitutes a current because of this motion of charge carriers, of minority carriers due to the field developed, and that we call it as drift current. They are drifting on either side because of the field developed. So, it is called drift current. So, now this is direction of hole drift and this is direction of electron drift. Now, as you can see here, the electron diffusion is in this direction and electron drift is in the opposite direction, which means drift current and diffusion current are in the opposite direction, either for electrons or holes, opposite direction. So, drift current and diffusion current are in the opposite direction. Now, as diffusion continues, what will happen? This width probably may increase because more and more electron hole pairs will recombine, and instead of only I showed you one layer of positive here and one layer of negative here. So, it may be another layer. So, another layer. So, what will happen? Because of that, this width will increase. So, as the diffusion continues, width of the depletion layer increases. As such, V naught and hence E increases, hence drift current increases. Therefore, drift current increases. Drift current increases. Now, this process continues until it establishes equilibrium position, equilibrium condition or equilibrium position, where you will have the drift current, I drift I will write, drift current equals the diffusion current, which means, of course, the both of them are in the opposite direction. So, I will put a negative sign there. So, I drift will be equal and opposite to I diffusion, that is diffusion current, and thus the junction is formed. Now, we know that the net current is equal to IE plus IH, and that will be both due to drift and diffusion, and I diffusion is equal and opposite to I drift, or other way around, I drift is equal to. So, no net current flows, this is the important point, no net current flows across the junction, no net current flows across the junction. When these two are opposite, then I becomes equal to 0. Therefore, there no net current flows across the junction. When is that? In an, what is the condition that we discussed? Open circuited or open circuit PN junction. That means a PN junction with no bias applied, that is with no bias. In the next video, we will discuss when we apply the voltage, forward bias and reverse bias conditions. Until then, keep watching, keep learning. Thank you.